Awesome. All right, welcome everyone to our third speaker event of the quarter. Today we are really lucky to have Professor Razvan Marinescu here at UCSC to come talk to our club. It's incredible for him to speak to us. I'm super excited to learn more about about his research and what he's done in the past with artificial intelligence and machine learning as it goes into the medical field. I think that those applications are extremely new, and I think he is one of the pioneers in this space. So I'm really excited. Please ask questions as the meeting goes on. You can either raise your hand, you can call on you through Zoom, put them in the chat, and I can pull questions through. And then as professor, you take like quick break in the middle. I can be kind of like a moderator in that sense. So without further ado, I'll take a step back. I'm excited, and yeah, let's do it.
Thank you so much, Rahul. This is great. So I'm excited to meet all of you. So maybe we can make it a bit more interactive as this goes on. Let's say we start. Can you allow me to share screen, Rahul? So just to say, so also feel free to write any questions on the chat during the presentation, like right away as you have them. So don't wait. I'll pick them up on the fly. Also, do raise your hand, like unmute yourself and ask questions right away. I'll take basically questions anytime along the way. Yeah, basically, let's get started. So let me just arrange a bit my setup here so I can move you all on this side. Yeah, good. I'm really excited to talk to you today. So my research is on in general about machine learning applied to the medical field, and I've worked on quite a few projects along the last 8 years now. So I've started doing this kind of research in 2014 when I started my PhD in London. I spent 4 years I was at UCL and did my PhD. Then I did my postdoc at MIT for 2.5 years. I was also working on a startup. So I have done some entrepreneurship as well. If you can ask me also about that, you're welcome to answer any questions. And also, I've been at UC Santa Cruz since July last year. So I just joined. And basically my work has been mostly on the machine learning applied to the medical field. And today I'm going to talk to you mostly about generation and analysis of medical images, and in particular using these kinds of models that we call Bayesian generative models. So basically the idea here is that we have generative models first. So you've heard of GAN models, flow models, any models that generate us new data as opposed to discriminative model. And here we have this keyword called Bayesian, and here this refers to Bayesian inference. So these models are able to work with probability distributions over the data and capture uncertainty, and they're quite powerful. I would say they're really powerful, because they can do a lot of things that normal non-Bayesian methods cannot do. So basically, okay, so the idea is that machine learning algorithms have achieved impressive milestones in the last many years on many tasks, on object detection, for example, on text-to-image generation, on image generation, as well as on text generation. But however, and also machine learning holds great promise for improving healthcare in the healthcare domain. So, for example, to enable us to diagnose diseases with unprecedented accuracy, given all the wealth of data that we have available in the hospitals today. And we see in the press many kinds of ways in which like artificial intelligence will impact healthcare into the future. And also they also hold the promise to be able to augment the doctors by providing them smart analytics to help them make the best decisions for the patients. But even though we have all this let's call it hype, in practice for many medical applications, these promises have not yet been fulfilled. So for example, the prediction of clinical variables has not always been working. So for example, we ran this competition called Tadpole, and basically in this challenge, the idea is that people would build machine learning algorithms to predict cognitive scores in Alzheimer's disease. And what we found, surprisingly, is that no algorithm out of all the 33 teams that participate in the challenge could predict cognitive scores better than random guessing. So basically, it was a really, really hard task, actually, for these machine learning models to do. So it brings us to, to kind of like question, why are they not able to predict, why is such a hard problem? And similarly, if you look on the right-hand side, these are the kinds of like image generation methods that have been, for example, this is a machine learning model that was used to generate brain MRI images. And these images are crude, they're not high resolution, and they're still mostly 2D. So we don't have high resolution 3D image generation models that work well right now. So for example, for brain images, and why are they not? We're wondering, why are machine learning models not working well on medical applications? And there's several reasons for that. First of all, we have a lack of good label data and good labels. So for example, for Alzheimer's disease, the diagnosis accuracy of Alzheimer's is just around 42%, because in practice, so this is the diagnosis of doctors that give us these labels. So in practice, only 42% of patients are correctly diagnosed with Alzheimer's. Most of the time, for example, the patients actually have something else as well. For example, Alzheimer's disease plus infarcts, or Alzheimer's disease plus Lewy bodies, which are these kinds of pathologies that appear in the brain. These kind of like bulbs that appear on the scan, and so it's much more happening. Sometimes around 20% of the time, they don't even have Alzheimer's disease at all. They have something completely different, like infarcts or Lewy bodies and so on. So, and another problem is that also these labels are categorical instead of being continuous. In practice, the disease is a continuous process that evolves over many, many years. Whereas what we get from doctors are just these thresholds of, like, for example, like, these crude categories of mild, moderate, and severe, instead of having some more continuous variables that we can map over the disease timeline. And we also have a lack of good input data signal because, for example, these scans have limited contrast and also low resolution. So we don't have often, like, very good high quality scans to start with that the machine learning models can leverage. So what can we do as a result of that? So for the problem of a lack of good labels, our solution is to perform unsupervised learning. So we don't rely on labels anymore, as in the case of supervised approaches. So therefore we do unsupervised learning. And in particular, we've done some unsupervised learning of what we call these continuous dynamics of trajectories of patients. And this is an approach we call disease progression modeling. And I'm going to talk to you about today. And for the second problem of the lack of good input data, the solution we proposed was to use image reconstruction techniques to perform image reconstruction using deep generative models that can basically, even if we have a low resolution or low quality scan, we can use machine learning models such as deep generative models to reconstruct a high resolution image that can then be used accurately to predict disease, to diagnose, and to do prognosis, and so on. So these are the two ideas I wanted to talk to you about today. Does it make sense so far? So do we have any questions? Does any of you have any questions so far on the motivation? And can I see some thumbs up? Can I see some sort of like yeses on the chat to get a vibe? Okay, good. I see one, I see two. Okay, good. So everyone is with me so far. Okay, so let's talk about the first idea, the idea of the disease progression modeling of Alzheimer's disease. So let's see how, first of all, why we want to do that and how. So Alzheimer's is a very devastating disease worldwide. So we have more than 46 million people that are affected right now, and this number is bound to triple to more than 130 million people within the next 30 years. And in particular, there's no treatments available that can stop or slow down the cognitive decline of the disease. And that's because all clinical trials have failed. Now, the reason why they failed, we believe the reason why they failed is that the treatments were not administered early enough. So And then the question is, how can we identify subjects early in order to administer these treatments? And the idea here is to use what's called a disease progression model. And let's see how does that work, and how do we build a disease progression model. So we have a subject with a brain MRI scan that comes to the hospital, takes a brain MRI, and then we segment something called the hippocampus. And the hippocampus is a structure in the brain that we know is affected by Alzheimer's disease. So we segment the hippocampus, and then we extract the volume of the hippocampus from the scan, and we plot it on this chart, for example. So here the y-axis is the volume of the hippocampus, and on the x-axis we have the timeline. And here at the beginning we have the disease onset. This is where the disease starts, and this is the timeline as the disease progresses. So we have one measurement right now for one patient. Now imagine the same patient comes back to the hospital 6 months later, takes a second MRI scan for a second visit. We again segment the hippocampus, as we saw here, and we extract again the volume, and we get a new measurement. And again, they do the same thing again. A year later, they come back for a third visit and so on, and we get a third measurement here. And now, given these 1, 2, and 3 measurements we have so far, we can start building a model of the evolution of the hippocampus in this one particular patient. And this is the evolution of the volume of the hippocampus. And now imagine you have a second patient that also, so a different person now comes to the hospital. Again, we do the same thing. We extract the hippocampus, and we plot the measurements for the second patient, and we get something slightly different now. For example, they have a different trajectory of the hippocampus. So for example, so what could be going on? Why are they, for example, different? Well, one reason why they are different like this is because, for example, in the second patient, the disease has already started. For example, the disease has started, let's say, 5 years ago or 6 years ago. So this delta T, this time lag, is given by the fact that the disease in this patient has already started 5 years ago. So what we can do in that case, we can basically align the data for that second patient to align with the first patient and build what's called the population model, where basically now all the subjects are aligned to have the same disease onset, and we have a population model like basically describing the evolution of this particular structure. And what can we do with the population model? Well, we can do early diagnosis. So then if we have a new patient, again, we have a new patient that comes to the hospital, they take a brain scan, we get a measurement here, we can predict with the model what is going to be the evolution of the hippocampus over time. And that's the idea of these disease progression models. So we can predict the evolution of the disease in new patients. And also characterize the disease at a population level, as we see here, but also individually in new patients. So we can also, of course, make this more accurate by analyzing all brain regions and sort of like do much more fancy modeling. Let me stop here again. Is everyone with me so far? Does this all make sense so far? Can I see some yeses or thumbs ups on? Yeah. Okay. Good. Yeah. So and this brings us. So one. This is what people have been doing in this research field in the last several years. And one limitation, however, was that they were using these predefined brain regions. So look how, for example, this brain was segmented into these predefined lobes. This is the cerebellum. This is the parietal lobe. This is the frontal lobe. Can you all see my cursor? I'm hoping you can. Again, can I see a thumbs up? Yeah, good. Okay, so you can see my cursor. These are predefined regions, but in practice, the disease does not often follow predefined regions. Sometimes they actually, the disease can affect just this half of the frontal lobe, for example, the upper half of the frontal lobe, or the lower half of the occipital lobe. So that's what we were thinking at that time a few years ago of trying to build a disease progression model that was not basically taking into account a fixed parcellation of the brain or fixed segmentation, and it was able to look at fine-grained patterns of atrophy in the brain. So basically, you could see these highlighted regions, for example, in red, which affect the brain severely, whereas, for example, the blue regions, which you can see here, which is this in particular structure here, is called the motor cortex. This one is not that much affected by the disease. So we wanted to see these kinds of really fine-grained patterns of atrophy in the brain. That was the idea, and that was the motivation. So how do we do that? So let me show you roughly the idea. So imagine you have two brains from two different subjects. So subject 1 and subject 2, you have their brain MRIs. Then you look at a particular location on the brain, it's called a vertex, a particular location, which is in correspondence across the two images. And you extract what we call the cortical thickness. This is like a measure of how thick the cortex is at that particular location. And then we build that kind of disease progression model I was showing you earlier, that kind of trajectory of how the cortex evolves over time, from different measurements of a patient. This is measurements from the patient 1, and this is from patient 2. And then if we zoom in on a particular location on the brain, this brain is made of many vertices. And these vertices have different colors. We're assigning different colors, like, for example, red, green, and blue, which will reflect how much the disease affects those regions. But in practice, we're going to model them within different clusters. So basically, we're going to do unsupervised learning. If some of you have some of you seen K-means or expectation maximization, can I get a thumbs up on that? So who of you? Okay, so one person has seen K-means. Okay, and EM. Okay, good. So some of you have. So it's the same idea. Basically, we have clusters in which we group similar points together into these kind of clusters according to the dynamics of the trajectory. So this is how the clusters look. So for example, we're basically doing a clustering over these temporal trajectories over time. So basically we have a cluster of red trajectories, a cluster of green trajectories, and a cluster of blue trajectories. And this is basically, these are all trajectories that are basically happening on the brain at these locations, and we cluster them to find the patterns, which ones are happening early on. For example, the red ones are affected very early, whereas the blue ones are affected much later. The atrophy comes later on in the disease. And then we also do, apart from estimating these trajectories, we also do this kind of temporal shifting of the subjects that I was showing you earlier, how sometimes we have to shift the data of the patients with plus or minus a number of years to align them to have the same disease stage. And we do this iteration on and on until convergence. So we're going to reallocate the points on the brain to different clusters. We estimate the actual trajectories for each cluster, the mean trajectory for each cluster, and then we shift the subject's disease progression scores. And we repeat this until convergence. And this is something that really resembles the expectation maximization algorithm some of you might have seen in machine learning courses. And this is exactly that, and we use exactly that framework, expectation maximization. And our contribution in particular here was that the model could now estimate the pathology evolution at each point on the brain surface. So it wasn't grouping anymore those kind of like lobes and regions together, and now it was estimating really fine-grained patterns of atrophy. So let's go a bit into the maths. how do we do this? How does it actually work? So we used what we call a generative Bayesian framework for this. So in particular, we assume that what we call the disease progression score for a subject I at a visit J was given by what we call a linear transformation of time Tij. So here Tij is the age of the subject I at visit J. So we assume that their disease score is a linear transformation of their age, where basically alpha here is the progression speed, is how fast the subject progresses, and beta is what we call the time shift, is how some subjects have early onset, some have a much later onset. And then we model the trajectory of cortical thickness at one location L on the brain. So basically we estimate that, we assume that the evolution of cortical thickness follows a sigmoidal trajectory like this. This is how a sigmoidal trajectory looks like. So basically it starts, initially the thickness of the cortex is high, and over time it gets lower and lower because of the disease. And that's how we model it. So that we assume that the likelihood of observing a particular measurement L at subject I, visit J, follows a normal distribution centered around the trajectory f, given a disease progression score from above, and having some parameters theta, k, and also sigma k. And then we basically extend this framework to all locations in the brain and all subjects. So basically, we take the model from before, and now we multiply for all locations L in the brain and all subject I at visit J. And we get the full likelihood of observing our data and also our parameter, given our parameters. However, now, so what we have here is that we have the data V, but we also have these Z variables, and these Z variables are modeling the assignment of points to clusters, like brain locations to clusters, to these red, green, and blue clusters. And these assignments are exactly the same assignments that, for example, you observe in the EM algorithm, where you assign the data points to a particular cluster. Those Z variables, they're exactly the same here. So what we have to do to get the partial likelihood, because we don't observe these assignments, that we have to marginalize them because these are hidden variables. So we get what's called the partial log likelihood of observing our data V, and these data V's are all the brain scans from all the patients, is now basically a product of all the locations, but now we sum over all possible clusters that this location L be assigned to, and everything else stays the same. Let me stop here for a second. Do you have any questions on everything so far? Let's try to make this a bit more interactive. So ask me anything that you don't. Maybe ask on the chat or unmute yourself. I'll wait a few seconds to have any questions. Have any of you worked on? Yeah. Well, what exactly have you worked on? What kind of models have you seen?
I don't know, regression. Just probabilistic modeling, but nothing like to this level.
Yeah. So, and what kind of model was it? Was it like a Gaussian mixture model, for example?
I don't even remember. It's been a while.
Yeah.
No, I've done something with Bayesian statistic modeling, but I don't remember exactly what.
Yeah. Somebody else? I saw another hand raised. What have you seen with Bayesian statistics, and what have you read? I saw another hand before. Was that you, Colin, that you raised the hand? Did you see some Bayesian statistics before, or did you? Yeah.
I gave a thumbs up. It was like more of, I did a little bit.
Yeah.
With Bayesian statistics, I wouldn't say like true research.
Does it make sense why you would use Bayesian statistics as opposed to something else? Actually, for all of you, does it make sense where you would need to use it?
Yeah, I can see its applications here. I think I can understand why. It's the same case with Cohen. I've used it before, but it was either a very long time ago, or B, it's just fuzzy in my brain as to where and when I used it.
Yeah. me say a few words about that. Like, why would you use it? So one reason is because of noise and uncertainty. So sometimes you don't know exactly, you observe some measurements, like for example, some data that you have, but that data could have noise already. So say, for example, look at equation 2 here, where my cursor is, this one. So we assume this is like these measurements that we see on the brain, follow a normal distribution around this. So basically, we have a line here, like some kind of spline, for example. It's called a sigmoid function, and we have noise around it. And that's basically, you can see, you can imagine there's like little points being spread around that region. So then that's one reason why you would want to use it sometimes, because there is inherent noise in the measurement process that you want to be able to capture. So uncertainty and noise that you want to capture with these kinds of methods. Does it make sense?
Yeah.
Yeah. And another reason why you would want to use Bayesian is because of, for example, hidden variables like this. You have some variables that you're not observing. Like for example, in this case, the assignment of the points to clusters. We don't know how these points are grouped on the brain. For example, which ones are the areas that are affected more or less. Like if I go back here, the whole point of this is to find the regions that are affected by the disease. We don't know them. So that's like a hidden variable, and you marginalize it in the Bayesian framework, but then you can infer those values. You can make a posterior inference and infer which ones are red, are severely affected, like affected very early, and which ones are affected much later in the disease, or not so much even. That's the idea. You have unobserved variables, unobserved data, to put it like that. And in this problem, and in general, many other problems, you have this thing happening. Does it make sense?
I think so.
Yeah. Okay. So let me move on a bit. So that was the idea with this project. So we applied this model on 4 data sets. For example, these 2 on the top are basically 2 Alzheimer's disease data sets, and notice how it shows where in the brains of the subjects this disease affects them most. Again, these red regions appear in this region here in the bottom. Is called the inferior temporal lobe. This is this region here, and this one is called the supramarginal cortex. And these are known areas that affect these patients quite a lot. This motor cortex, you see these blue areas here and here, these are generally less affected. So we know that the motor cortex that handles motion of the patients, and these are less affected by the disease. Notice on this one, this PCA, this is called posterior cortical atrophy. And this is basically a different type of disease. And basically this is known to affect the posterior part of the brain, and this is exactly what we observe, that our model actually does capture the pathology, especially in the back of the brain, the posterior part. Whereas, and for example, when we look at a different data, like for example in positron emission tomography, which these are different kinds of scans that capture amyloid aggregation. This amyloid is a toxic protein that aggregates in the brain. We see a toxic protein especially in the front part of the brain, as well as in this supramarginal cortex is called. So that's the idea. You see how the brain this model can capture different patterns of atrophy, and we can get these nice contours of severity, sometimes from like highly affected regions to much less affected. And these contours again are basically, these are points that are basically sort of like using this framework to cluster that. So these kind of clustering these trajectories over time. And of course, we did a cross-validation basically by doing different splits, and you can see how what kind of brain patterns we get over different cross-validation splits, and also the trajectories over them, and they were quite similar over these splits, over these these kinds of patterns that we observe. So that means the model is robust to these kinds of changes. But let me now tell you. So this was this was all great, and these models in particular require good quality data to be able to run and perform registration and extract these disease markers. So now, however, the question is, can we do such a modeling when we have much more limited resolution and contrast? And this kind of brings us to our second project that I wanted to talk to you about today on image reconstruction using deep generative models. So here the idea is that we have a low resolution scan and we're trying to reconstruct it to get a much higher resolution, like brain image that's less free of artifacts and so on. Well, this is the idea. So the idea is to perform an image reconstruction in particular using pre-trained generative models. So for example, in the literature, there were several generative models like StyleGAN, and now more recently we have like Stable Diffusion and so on that can generate really nice high quality images. For example, like this of people, of objects, of animals, of objects and so on. And the idea was to adapt these models to perform medical image reconstruction. So again, given a low quality scan that has noise, that could have a scanning artifact and so on, can we reconstruct a high quality scan using these AI methods? And that was the idea. So, and in particular, the current methods of image reconstruction had several limitations. In particular, they required large computational resources and data. They also had distribution shifts that require retraining, and they're also anti-causal. So let me talk a bit about what I mean by these. So in particular, the state-of-the-art deep learning methods these days have really large computational requirements. So we need a lot of computational time, we need advanced hardware and large data sets. And of course, most computation now runs on the cloud, on these big clouds in these big data centers that you see here. And there's currently very few labs and companies in the world that have the resources to train these state-of-the-art models. For example, for StyleGAN, we need something like 9 days to train on 4 GPUs, which is still a lot to leave it running for 9 days. And if you have all the required GPUs and so on. For example, for GPT-3, it required 355 years on a single GPU of training time. So these are huge resources and training times that only a few companies in the world can afford to. So what are the solutions in that case, especially for more like academic groups or for smaller companies that don't have all these big and huge resources and money to spend, like millions of dollars to spend on this? And the idea is to either, for example, adapt previously trained models, so models that already exist. We can basically adapt them to solve new tasks, or to combine smaller models into larger ones. And then some other problems, for example, in a scan or software upgrade, we have to reach a model every time. And sometimes these changes can also, or shift or changes can also be continuous. For example, the population that we're analyzing is getting older and older over time due to better healthcare. So if you trained an AI model 5 years ago on a population, for example, in your hospital, maybe 5 years later, that population could be different because maybe they got older, or who knows, you had an influx of new people in that area, and these things, and you have to, as a result, retrain your machine learning model just because your input data has changed. And I'll skip a bit over this, and also this, and let me tell you. So, and in particular, there were some methods that could use pre-trained generative models to perform reconstruction. So, for example, look at this. This model was image to StyleGAN++ from 2020. So it was able to, for example, fill in, for example, like these images, do in-painting, and get quite a rather good reconstruction. Of course, you can see some errors and differences, but it's still not quite relatively reasonably good. And this other method was able to do super resolution. But the problem they had is that they couldn't characterize uncertainty and recover multiple solutions. There's multiple ways in which you can fill in something like these kind of like chunk of an image, or you can. So that was the idea. The idea we're trying to construct a Bayesian formulation that could characterize the posterior over all the potential solutions in this what's called an inverse problem, which is an ill-post problem. So how we did it is that we basically took a pre-trained generated G, which was, in that case, StyleGAN2 in our work, and back then when we did this work 2 years ago, this was a state-of-the-art model. Back then we didn't have stable diffusion and the more recent methods, but the idea was you had a latent vector W. You passed it through StyleGAN to generate, for example, a full high-resolution brain image. and then you pass that through a known corruption function. Like, for example, you downsize the brain image with a convolution kernel, for example, like a downsampling kernel, to get a low resolution image. And then you take your input image. So this input image is what you get as an input, and compare that input to the low resolution simulated image that you submitted through the pipeline, by the StyleGAN network. And then you compute a loss function. So you take the two images, you overlap them, and you try to find a loss between the input and the low resolution. And then you use backpropagation in PyTorch or TensorFlow or your favorite framework to flow these gradients all the way back to the latent. So we don't flow the gradients to the weights of the network, we flow them back to the latent vector. And the idea is to optimize the latent vector so that it would give you a simulated image that is as close as possible to the input. Does this make sense? What I'm saying here? Do you have any questions on this? Okay, so that's the idea, but so we're trying to simulate an image that is as close as possible to the input. But by doing that, going through this and simulating such an image, we are able to then like go back and take the high resolution image, and that gives us basically the reconstruction of our problem. We get back the high resolution image as a result by achieving this, by solving this problem. And not only that, we can reuse this for other types of reconstruction. Like, for example, if we want to do in painting, or for example, if you want to, if you have motion, if you for example do something called like undersampling in MRI scans, it's basically where you don't measure all the pixels in the image, but only some of them, like 10% of them. You can basically reconstruct the image from these kinds of tasks for free with the same generator. You don't have to retrain a generated model. It is exactly the same model. And this is in contrast with previous methods that, for example, were basically trained on a particular data set of, for example, brain images, but also specific to a particular corruption function. So, for example, one model could only do super resolution, whereas another model could only do in painting. So we can do multiple tasks, both of these and many others, with the same model and with the same framework. And how it worked, again, is by simply leveraging the powerful Bayes theorem, and particularly computing what's called the Bayesian maximum a posteriori estimate. So the idea is to want we optimize W, which are the optimal W star, which are the optimal latents, by an argmax over P of W, the prior over W, and the likelihood of observing an image given that particular W. And here, for an uninformative prior P of W and a Gaussian noise model, which is pixel-wise independent, we get that this optimization, that W star, is basically the one that minimizes the L2 norm between the image, this low resolution image, this is the input image, and the low resolution simulated image. This is basically F composed with G of W. So G is our generator here, and F is our known corruption. So basically F composed with G of W is this low resolution image. So then we basically take the L2 norm between the input and this image, and that's our loss, and we minimize the W of this. And this can be optimized with stochastic gradient descent easily, actually. And once we get W star, then the reconstructed image is basically G of W star. So we get an optimal latent at the end of the day, and we pass it to the generator G, and then we get the high resolution image that we return as a solution. So this is the reconstruction of the input image that we pass in to the method. So this is the idea. So we started from the original StyleGAN 2 inversion code, which was doing something like this. So we have an input image that is low resolution. For example, this is the true image on the right. And this is what the original StyleGAN 2 inversion code was doing. So you see quite a lot of artifacts. It wasn't this particular procedure of inversion. This was not designed to perform image reconstruction. It was designed to just invert full resolution images. So just to do an inversion, but here we're using it for reconstruction, for a much harder task. So we had to do several changes to this. So in particular, this was the actual minimization function that they used, which was very similar to what we showed before. The only difference that they have this network phi, which is basically they also pass it through a perceptual network, the image to a perceptual network to compute what's called the perceptual loss, which is basically an L2 loss just passed through the perceptual network phi. But otherwise it's the same. And in particular, they had these eta vectors, which were these noise vectors that we had to remove. And that was simply because of the design of StarGAN was as such. So we removed those noise vectors, and this improved the reconstruction somewhat. And then we did some more optimizations where we basically optimized the latency at all resolution levels. How StarGAN basically generates the image in increasing order of these resolutions in high and high resolutions over time. So we optimize the latency at all of these resolution levels. Now we have one latent W1, W2, up WL for each resolution level. We added a pixel-wise loss in the original input space. So now we don't have just a perceptual loss, but also a pixel-wise loss. And you can see the results, how the results are starting to improve for some of these data. For example, for super resolution, you get better, crisper images. And then we also added a Gaussian prior on the latents to stabilize somewhat especially for these ill-posed in-painting tasks. For example, we have a missing part of the image missing. And also we forced the latents to be collinear. And this also improved the results even more. So now you get much more regularized reconstructions, for example, for super resolution, as well as for in-painting. And still, of course, there is still much work to do, but we believe this was the limit we could have done at that time, mostly because the generator itself didn't have enough capacity to capture these really highly diverse data sets. But at least with this was the best we could do at the time with that current technology. And using it for reconstruction. So, and well, of course, we can actually express a full likelihood. This is basically what is called like likelihood. No, this is basically called an error term, like a loss function, but we can actually express it in Bayesian terms. And this is something we have in the paper, but I'm not including it here in the presentation just to keep it a bit more simpler. But this was the idea. This was the very foundation of the method, and we applied it on several tasks on super resolution, and we got improved results compared to the state of the art at the time. So this was state of the art at the time, like ESR GAN, SRFBF, and POST, and we got much better reconstruction, especially for very low resolution images like this, to try to reconstruct such images which are very pixelated. Notice these are our results, for example, as compared to ESR GAN and SRFBF, for example. And whereas POST reconstructs something completely different, so it has very low consistency, it's called, compared to the input. And same here for even higher resolutions. And same for medical data sets. So we apply this also on X-ray scans, chest X-rays, on brains, because our motivation was to get this working on medical scans in particular, to be able to make them better and faster and help doctors. So, and again, we got good results on these medical data sets. And we also achieve the same thing for in-painting. We are able to in-paint really large masks. If you look here, for example, so half an image, these are the original images on the left. So what we actually observe is only, for example, half of the image. Like those in-painting methods back then were failing very poorly. For example, especially if they're only doing something around the edges, but on the inside, they weren't able to capture any structure. But our method was able to understand the high-level structure, for example, and still reconstruct the face. Although it's not fully, you see, it's not fully seamed with the other half. Basically, you get, it's able to understand the general structure. This is the face of a person like this, and is able to capture quite a lot of good patterns. And same for the other ones. And same results on medicals, on brain scans. Again, this was the state of the art at the time. For example, for a brain, our method was able to fill in quite reasonably what the left half, for example, of the brain was in this particular case. And same for the chest X-ray. Does it all make sense? Can I see some thumbs ups? Can I see some, or chat messages? Yeah, okay, good.
I had a quick question actually.
Yeah.
Could you go back a couple slides real quick to the I think it's a couple more. Yeah, this one.
Yeah.
I wanted to know or the next slide.
Uh-huh.
I wanted to know how much does resolution size impact the actual output of the model? Because when I look at the images here, it feels like, and at least I know you mentioned it, where the higher the resolution, the more accurate it is. Is that because you have more pixels to kind of play with to kind of understand? So you get a more accurate representation?
Yeah. So imagine that this is the input here. For example, you have more pixels. You kind of get an idea that this is like the
Right.
face of a little girl, but here
Right.
it's so hard you can barely see some kind of
Right.
structure. So the method has to fantasize, hypothesize what could be basically, what could this be actually? What could this image
Right.
be? Does that make sense? So it
Right.
needs really strong prior knowledge.
Right. And then, so that's why when you have a larger mask, that's this for the same reason. If you
Same
have to do that,
reason. The method
Right.
has to imagine, has to
right,
be creative. Like, what could that be? Like
Right.
it's not learning from, same here. Like, big mask. What could be on this side? Could be so many. It could be. You see, this was even actually they had another person sitting next to them. But like.
right,
There could be all kinds of things, like they could be by themselves, and so on. So the method has to create that and sort of like, and for that, it's such a hard problem. You need very strong prior knowledge for that, kind of about the problem and the domain of this problem.
got it.
Does it make sense?
Yeah.
And this
makes
is exactly where a setup where something like, you cannot solve this with supervised learning because it's, you have to have a strong prior knowledge of that. And that's why you need something like a Bayesian framework for this and something like, and this is where you could, if you have, by I'm going back now a bit, because the idea here is with this generative model on the left, you're trying to learn all the space of and this is the prior knowledge you're learning. And then from this corruption, you're basically able to, to sort of like plug in this corruption module, small corruption module, and then you can basically reconstruct, given your prior knowledge, because this G is pre-trained, you can reconstruct, this particular task for this corruption. You can revert the corruption basically, if that makes sense. I'll stop here for a bit to let that sink in. Does anyone have other questions?
Makes sense.
Yeah, makes sense, Raul. Yeah, good. So yeah. Let me show you something more. So I'll skip that slide. So let me show you this one. So the idea in general is forget about the equations for now in the title. So look here at this. Look at this very coarse grain, very like pixelated image. So basically, I took this image, this true image, and downsized it by extreme factor by 256. So basically, you end up with a 4x4 pixel image, like 16 pixel image, like this, right? And then the idea is I apply the same method again, like, given these observations, give me like, the possible faces that could be this person, basically, like that could be. And look here. So basically the method can then not only reconstruct one solution, but multiple solutions. So basically this is, it captures like a distribution of potential images that can map, given that down sampling to this. So basically, these are samples from that distribution, sample solutions. And this is, for example, the estimated mean, the mean, the mean vector of that distribution that, that captures the solutions. And this was the true image that was used. Does it make sense? Or for example, here, look at it in painting. Again, the same thing in painting here. We can get a mean vector a mean reconstruction, but also samples around that mean, around in that abstract distribution that you imagine, basically, you know. So, and you see some of them are not that good, you see, because the hair cannot be changing colors in the same person, but some of them are quite reasonable. Like, for example, this one, you see the sample is quite good, you see it's matching quite well, or even this one to quite reasonable extent. And of course, if the method was to work perfectly, like you would only give you samples that actually work, that actually fully, completely match, and perceptually you won't tell a difference. But there are multiple ways, multiple solutions to this in which you can basically reconstruct. That's the whole idea, and you want to capture all of them in a distribution, in a posterior distribution. Does this make sense to all of you? Yeah, can I see some thumbs ups? Can I see, yeah, something on the chat? Yeah, good. Okay, so let me ask you a question. How many of you have heard of variational inference? Have any of you seen that? One person? No, nobody has seen variational inference. No, yeah, okay. So variational inference is a really powerful technique, but it's quite advanced, basically. So you will cover this in very advanced machine learning classes, statistical machine learning classes. The idea is that you have this idea, this notion of a distribution of solutions that you're trying to learn, and you're trying to learn that with what is called a parametric distribution. So basically, this P of W given I, this term here, is basically that true distribution of solutions, the true ways in which you can fill in these images, or these true solutions, that basically these images that map to this downsampled image. That's a true one. And you're trying to approximate that P with what's called a variational distribution Q. And this Q distribution is kind of an approximation to P that you're trying to model. And you're trying to model this approximation and by minimizing some kind of notion of divergence between the two distributions. It's like basically like a loss function across distributions. The more dissimilar these distributions are, the higher the loss or the cost. And this metric, this distance metric or distribution, is called the KL divergence. This KL divergence is some kind of like distributional metric. It's asymmetric, actually. I won't go into details why it's asymmetric, but basically if you flip the order of the position of them, you actually get a different measure. But the idea is that it's a distance it's a metric of distribution. So the more different the distributions is, the higher, you know, the distance between them will be. And it has a particular formula which looks like this. So it's an integral over all the vectors W, and these W's again are the latents of our model, of the variational distribution Q of W given theta times the log of the ratio of Q over the ratio of P of P basically. And here this is P of W, the prior, times the likelihood. And this is actually equal to the posterior. So this P of W given is the posterior of the parameters given the image. And by Bayes' rule, it comes up in the bottom here as the prior times the likelihood. And the idea is that now that this integral is intractable to compute, it's very hard. No, it's not very hard. It's just impossible to compute it tractably, this distribution. So you actually have to approximate that integral using what I call Monte Carlo samples. So basically, you take many samples of W, and you basically you take some samples of W from this distribution Q here, and basically just compute that ratio from that from those, given those samples W, you just compute that ratio, this log ratio of Q over P, of the posterior of Q over the posterior of P, and this is what you get here. So we take a sum over all the samples W that you take of the log of Q minus the log of, so this is the top of the fraction minus the bottom of the fraction, log of the prior minus log of the likelihood. And this is basically, and then you minimize this over your parameters theta. And here theta are the parameters of this variational distribution. So this distribution, for example, is a Gaussian distribution. You can make it a Gaussian distribution, for example. You can choose something else, something even more fancy than that. So the Gaussian would have a mean and a covariance matrix, and those are the parameters that you minimize here. That mean and the variance of that Gaussian distribution. And this is what you see here. So this estimated mean was part of these theta parameters that we estimated with this equation. Did anything make any sense here? Because I know it's very hard. I know, but did anything make sense? Did what? Yeah. Do you have any questions? Yeah. Do you have any questions on this? Like how variational inference works? Yes, a complex, but I get the overall picture. Yes, yes. A lot of motivation to take more stats courses. Yes, yes. So it is, yeah, this thing does include advanced statistics and advanced machine learning. Yeah, so you see a lot of this like KL divergences when you work with distributions, where you kind of like try to assess how similar two distributions are. You'll use something like the KL divergence. And there's other ways to, other metrics as well. But that's the idea, yes. And the same idea, the scale divergence, also appears in variational autoencoders, in VAEs, because they also use a variational inference on autoencoder models. That's what the variational autoencoders are. So you see this also in many other ML models. But yes, I know it's a bit more complex, but they're very powerful techniques, very powerful for basically solving such hard problems, like for example this, like when you have very limited data and you're relying on strong priors that you're also learning with the neural networks, also based on data. That's the idea. Yeah, so again, and the same approach again on other kinds of images, including medical images. So the same thing you can do on medical scans, chest X-rays, brain images. Again, you have you're trying to fill in half of the image, for example, and you can get the mean and the multiple solution, multiple samples, like which are basically potential ways in which the network can fill in that missing half, for example, or reconstruct the image. And also the method is, of course, is still like, it still has limitations that we still need to address. And for example, one limitation is that there's so much heterogeneity in these images that sometimes, for some inputs it can still fail. Like for example, this is an input of an image in which it still wasn't able to get crisp solutions. So we still see these jittery artifacts here for something like this. Whereas a true image was this one. And sometimes the reconstruction can still have some inconsistencies with the input image. So the result can be inconsistent. So for example, if we take this input image, we downsample it, like you see here, for example, and then we reconstruct it with our method, and then we downsample again the reconstruction. The reconstruction after we downsample it should be exactly the same as the input in theory, but in practice, look how the downsample reconstruction is a bit different than the actual input image. So and you see here the difference map. Sometimes the edges are not perfectly reconstructed. So it means there's some inconsistencies between the reconstruction and the input, or some loss of fidelity is called, and that's because the prior is basically pulling away the result towards the prior knowledge, to try to give it more regularity. And there's basically, at the time, there was nothing we could do, at least because the problem was that the generated model we were using, StyleGAN, we didn't have enough capacity to cover all these different images. And even so now things have gotten a bit better with the newer models like Stable Diffusion, but it's still, I wouldn't be surprised if the same thing would happen even if we try to plug in a Stable Diffusion model instead of StyleGAN, and you will still get some of these kind of artifacts, maybe less, but still they would exist, because again, the model would not be able to completely generate any kind of image that exists in the world yet, but it might in the future. So that's the idea, and also depends on what kind of corruption you apply. So there's a lot to be said here, but I'll just stop here. And so that's Do you have any questions? How much time do I still have? Oh, okay, it's already 7:05. So maybe how about I stop here and yeah, take any final questions, or otherwise, yeah. What do you think, Rahul? How do you have a final Q&A at the end, or? Yeah.
We could do a final Q&A here. It is 7:05. We can do a quick Q&A, and then we can wrap it up.
Yeah, okay.
Awesome. So I think a lot of my questions throughout got answered. I think learning about just how all this works was really exciting to me.
Yeah,
Definitely.
I hope, yeah, I know it's a lot. It's a lot. I hope it, yeah, it was able to kind of, get some, get an idea at least, of how, some of these things, work here.
Right. I think it's definitely something that I want to continue to kind of pursue, because I think this entire field with like image generation and reconstruction is something that is just really cool, and I just want to see how it continues to work and how it continues to be improved on. In the chat, we got thank you for all the insight. Very intriguing.
Yeah. We have a question from
Cohen.
Yeah, I'm curious. So, for me and for a lot of people just entering and that want to do more AI, and so when it comes to taking AI classes, obviously there's the 140 series and all of those classes. Do you have any suggestions on which order to do them, or which one, what they are all like specifically about?
Yeah. Actually, so, first 140 Intro to AI. I would say that start with that one. Start with Intro to AI, then go to like 142, basically like machine learning, or 242. So I'm I've also taught the grad classes at 242. So I would say that one next, like machine learning. And then go into more the application specific ones, like for example, go into computer vision, natural language processing, applied machine learning. Also, there's another course, I think I forgot what was the code for that. That's what I would say, the order: Intro to AI, machine learning, and then the applications ones, like applied machine learning and computer vision and natural language processing. And but similarly, there's the other path, like I would say in parallel, to try to follow also the more like so for example, if there are more kind of like specialized courses, grad classes, for example, on Bayesian statistics, like for example, I know the stats department are offering some of those. Those would be very good to take, because those cover a lot of these like Bayesian statistics, and more say then there's also there's many other things like you could take, like for example, I found really fundamental some courses on so that I took back when I was in London at UCL, for example, on graphical models. That was a really good course, for example, that I took back then, and it taught all kinds of like powerful models, like again, hidden Markov models, any arbitrary like causal models, it was sampling in these graphical models. Like you learned like the junction tree algorithm. You learn a lot of things that are not normally taught in the more like standard like neural network courses, like deep learning courses, and those I think are quite important to cover also.
You brought up the CSC 242. I think you taught it before.
I taught that. Yeah.
How is that course, I guess, different from the undergrad classes? And do you think it'd be reasonable to take for undergrads?
You can. So they go a bit more in depth into some. It's basically very similar. So 242 is the grad version is very similar to 142, the undergrad version. It's basically the same content. It just goes a bit more in depth into some topics, because it's a grad level course, but just a bit more deeper. But otherwise, it's the same kind of storyline, the same material. Just goes a bit more in depth into some of them. Like that's the idea. So you can, if you want, you can take. It's if you're an undergrad student, you can take. Of course, you can enroll officially for the undergrad version. I don't know if you can be allowed to take the grad classes. Maybe, but you can still audit them. For example, you can go and audit that class, for example, and like, yeah, and you can do that. You can audit other classes, the other courses as well. Yeah, again, the more applied one.
Yeah, that sounds great. Thank you.
Yeah, yeah. Any other questions? No? Okay.
No other questions?
I got one more before
Yeah.
Raz's, but it's not quite relevant to the club or like the
Yeah.
AI stuff.
Yeah.
So I'm trying, me and another club are trying to start a research lab. And so we were wondering if we can get some of like, have like a meeting with you to talk about the ways to go. Like I talked to Leilani earlier today. So I was wondering if I could set up a meeting with you to go over details and see if you have any advice.
Say again, are you trying to start a lab or what did you say?
Yeah, we're trying to start like a student-led research lab. Obviously, it's not going to be as big or prestigious as a regular research lab. It'd be a lot smaller size.
Good idea. That's actually a very good idea. I like that. Yeah. Let's meet up. Let's meet up and discuss. Send me an email. Yeah.
Okay, yeah, I'll send you an email.
Yeah, perfect. Okay. Yeah. I like this idea. That's and I know some. That I know there is some kind of like a student-led also like a lab online. I know it was called Euler AI. I don't know if you heard of it. They were on Discord basically, and they were kind of like working together on some projects like around GPT actually. I don't know, have you heard of that?
Is that related to Santa Cruz, or is that just like nationwide?
It's not, no, it's like some kind of international. Basically, there's a few students from like around like different parts of the world, like yeah, and they were working together on papers basically. Yeah.
No, I haven't particularly heard of them before. That's really interesting.
Yeah. So that's something also maybe you might be good to actually get in touch with them also. But we'll talk more when we so send me an email. We can meet up. Yeah.
Yeah. Perfect. Yeah, that sounds good.
Yeah. Okay.
Awesome.
All right.
Any other questions? Going once, twice. And yeah, awesome. Thank you so much for coming in and speaking to us. I was really, really interested and fascinated in everything you had to say. I know everyone else here was as well. Yeah, just thank you, and thank you all for coming out.
Yeah.
Awesome.
Yeah.
And